Swayam Prabha. Digital India. Educated India.
And welcome back. So in the last few modules we have studied different types, different components of robots, maybe a few types of sensors that we have learned, few types of actuators we have learned. We are now introduced to robots almost. So continuing further with the sensor module, so we have already gone through position sensors, various types. We have seen how a velocity sensor works. We have seen accelerometer, how it can be used like a force sensor. Continuing further, today we'll go through a leftover portion of that, that is proximity sensor, that forms a very important type of sensor which just checks the events. Okay, just checks the events which is happening around. It just tells us whether it has happened or it hasn't. Okay, so instead of going in an analog way, most of the time this type of sensors work like just a digital sensor, just as an indicator. Okay, so yes, today we'll be discussing upon inductive sensor, we'll discuss about capacitive sensor, okay, and few types of force sensor. That is one very broad class of force sensor is strain gauge based sensor, and which is most widely used in the industry also. So we'll be discussing upon that. So okay, so let us move ahead. Okay, so to begin with, we'll start with a non-contact type of sensor, that is inductive and capacitive sensor. Inductive proximity sensor works very much like our induction heater at home. The first part of the sensor that you see here is this one. So overall it is part of a circuit which is here, that may be called as an LCR circuit. So if it is an LCR circuit, so any current which is there, it cannot be just an static. If you just start with an oscillation, it is very much like a spring mass system. So provided with some external energy that is provided through external supply, there is an oscillation which is happening all the time over here. So you have a current oscillation which is there, and that is picked up across the capacitor which is here. Okay, and you have a coil which is here, you have a coil which is here, that basically is an inductive coil. So it transmits flux outside to it. Okay, it transmits flux outside the sensor also. So anything, if it comes here, which is a metallic target, if it is there, so if it finds any metallic target somewhere nearby, so there is some change in flux obviously. So it is treated like a load for this type of sensor, and there is some change in the behavior of the loop current which is oscillating inside. Okay, so there is some internal oscillator, there are some resistance which is here. Okay, there is capacitor which is here. Across the capacitor I am just measuring the voltage. Okay, this measured voltage is not just a source where we can measure voltage. Okay, so it is also providing supply to this LCR circuit, the external power which is there. Okay, and finally this sensed voltage is not significant enough to be transmitted, so it is converted to a digital form using analog to digital converter. Okay, and there are some driving logic which comes from here, that may be a triggering circuit. So if at all we want to count the event, we need to have a switch which can give me a square wave kind of signal, which is finally picked up and it is transmitted using this processing logic. So this is a gross layout, not exactly this one. The internal circuit may be quite complex, not this. This is just to get the philosophy of it, that you have a LCR oscillator, you have an LCR oscillator with an induction coil over here. Okay, so any target in front of it will change the oscillation frequency or the behavior of the voltages which are available over here. So you just pick up that voltage, you convert it, you make a switch trigger a value of in a way like high or low, and finally that is transmitted. So this is how it works. It can work within the range something around 1 mm to 60 mm. That is the normal range. You may see a few more mm which may be covered by some manufacturers. Okay, so output is normally digital, and that is in terms of high or low signal. In industry it is like 24 volt or 0 volt. Yes, it can be normally closed or normally open. What does it mean? In any digital sensor, okay, so if at all there is a target, it gives you a high signal. It may be possible that you use it like normally the signal is high. If it sees any target, it turns to low. So either way it is possible. So just look at the theory now. So it has an LC oscillator circuit. LC is L for inductance, C for capacitance oscillator circuit. It induces eddy current in the target. It is like eddy current that is coming here due to this flux which is changing here. So it induces an eddy current here in the target that causes loading to the oscillator. So you must have noticed when you put a utensil on top of your induction heater, then only it turns on, it detects the target. So that is loaded, and then it starts drawing electricity from your source. Okay, so same way it is loaded, and that load is now checked at this target point. Okay, so this is the point across which if I keep on checking the voltage across that, so I can come to know, I may come to know that yes, there is something which has come now. Okay, so this is how it is triggering the circuit. Okay, so sensing coil that picks up the change in oscillation amplitude, change in oscillation is picked up, and finally it is processed and trigger is set. Okay, a trigger level is set as a threshold compare level. It is normally an op-amp comparator which just checks if value is above certain threshold, you give it a high signal. Okay, so yes, this is normally a solid state signal conditioning circuit, okay, and a communication unit. So there is a communication unit which can transfer it like a digital signal, high or low, or it may be an simple another way of conversion sometimes, like I2 signal or maybe a serial signal or something like that, but that is not much necessary here. You just have 3 wires, one to connect it to the ground, other one to voltage, that is the supply voltage, other one is just for the signal. Okay, so these are mostly the 3 wires which are there. So look closely, it looks very much like this. Okay, very much like this. Okay, so it has 2 cross nuts which are there. So if you can have some fixture over here to hold it in place, okay, so that you can tighten it and place it thoroughly. And then normally they have 3 wires at the end, 3 wires as I told you. So one of them is supply voltage, that is 0 to 24 volt. Okay, so yes, and this is the 0 volt, that is the common one which is ground, and one of them carries the signal, digital signal out, maybe normally open or closed type. So this is how it looks like. Okay, so yes, this inductive sensor has got few advantages and few disadvantages that we'll be discussing now. So these are very accurate as compared to other technologies, okay, which are there in the industry, like capacitive sensor, maybe ultrasonic sensor. Okay, so as compared to them, these are very accurate, and they have a high switching rate. Why it is required? Maybe you have just like this one, you have a conveyor here which is carrying an different objects which on this floor. Okay, and then you have multiple types of sensor from the top, from this side. Okay, so all these may be capacitive, may be inductive sensor. Those are all proximity sensor, because this platform which is moving, conveyor, is quite wide. Okay, so you may have different sensors from all around, so that you don't miss out any object which is moving on it. Okay, so this is one maybe a possible arrangement. Other one is a flywheel which is rotating, and you have these kind of protrusions which are there. Okay, so what are these? So they are the object. They behave like an object. If it comes closer to this proximity sensor which is here, so it will count it as high. So number of high counts will let you know the position of this rotating flywheel. So these are few arrangements and some applications that that is there in the industry quite commonly. So yes, and now you see, if this shaft is rotating at very high speed, what will happen? You will see a very high frequency of high and low signal. Okay, so if this inductive capacitor doesn't have this high switching rate, so it will behave like a constant high signal which comes at a high frequency. That should not be the case. So this is the reason why a proximity sensor should have a very high switching rate. Okay, so it can work in a very harsh environment. So normally industrial environment like this, they have vapors, they have moisture, they have dust, they are prone to noise. So those kind of environment is very easily accommodatable on at least induction sensor, okay, inductive sensor. So virtually unlimited number of operating cycle, because nothing changes within the circuit, right? So nothing is getting wear or worn out over the time, because there is no physical contact which is there. Not even the internal source is there which is changing its amplitude also. So everything remains inside as intact and nothing is changing. It is solid state device. So normally these type of sensors, they have unlimited number of operating cycles. So over the period of time, it almost sees years. Okay, so yes, they are very low cost, because hardly there is any circuit. You can create your own circuit at your lab and you can just test this kind of circuit. Okay, so yes, they are very low cost. They have almost like no maintenance. You just need to fit it and forget it. Okay, there are few disadvantages also. It can detect only metallic target. The way it works, eddy current can only be induced on a metallic target. So that is the reason it works only with the metallic target. Okay, that covers a wide range of objects which are there in the industry. So yes, it works quite commonly with those. Okay, so operating range may be limited, yes, because you see eddy current, that flux lines cannot go quite far apart, or it may be not dense enough to trigger that change. Okay, so that is the reason this is not quite, they don't have much longer range. Okay, so yes, now going to capacitive sensor. This is almost a similar way it works, with a similar range and similar output type. This also triggers a level somewhere within the LCR oscillation circuit. So just like the earlier one, this also has an oscillator. This also has an oscillator circuit that is sent to a current sensor which is here, and there is a capacitor plate which is here. So what is creating that change is this internal plate, capacitor plate, works like a capacitor along with the external target. If at all you see a target, there is a capacitor. If at all there is no target which is nearby, so there is no capacitor, and this air in between, this works like a dielectric. Okay, so yes, you see now the target, if it comes closer, the capacitance changes. The capacitance which is here, this changes. That creates the change in the coil frequency and the threshold voltage which is there. So yes, that also is picked up somewhere, and it is detected like a threshold beyond which you just have to give it a high signal, and finally they are given out with from the sensor like a DC output. So philosophy remains the same. Only thing here is, instead of using a inductor, okay, now you are using a capacitor that changes. Okay, so yes, the internal capacitor plate is there, and you have an oscillator which is there, and there is a threshold detector which is there, just like inductive sensor. Okay, and the output circuit simply allows the data to be transferred to longer distances. Okay, it changes the level to 0 to 24 volt. So 0 or 24 volt if it is digital, so it is high or low signal. Okay, so yes, we'll also discuss some advantages for this. This can detect both metallic and non-metallic target. Okay, how? Because so anything which comes in front of it, maybe mouse which is there somewhere nearby, so that also can change the dielectric constant which is there. So it can detect the change very easily even if it is not a metal. High speed switching, this has a very high speed switching just like inductive sensor. I think it is even better for this. Okay, so it has a very good resolution. The range can be adjusted. Okay, you can let us say you are now sensing from 0 to 5 mm, you can adjust with some potentiometer which is there sometimes on top of this kind of sensor. So you adjust that, you can adjust the range from 5 mm to 10 mm, 10 mm to 20 mm. So anywhere in between it works. Okay, they are very good type of sensors in terms of power uses. They hardly consume any power when it is idle. It is also used on mobile devices, mobile robots also, because they carry battery along with it, so you have to work with battery for quite longer amount of time. Okay, they can detect targets through non-metallic barriers also. What does it mean? Let's say you have a sensor, with which is expecting object somewhere over here. Okay, any object can come in this range, but fortunately or unfortunately you have a barrier which is here, and this is a non-metallic barrier. Okay, so even if this object comes now with this barrier over here, it can detect. Okay, if it comes here, there may be some change in the tuning distance which we have done. Let's say I have tuned it to work with 50 mm over here. Now it will work with lesser distance, maybe 25 mm. Now the object has to come in order to get detected. Okay, so that distance may vary, but yes, it can use that kind of thing. So this allows you to seal this whole of this sensor within the robot. Okay, so it can be made very good IP enclosure, ingress proof enclosure, so that dust and water that cannot get into your robot. Okay, so yes, because anyway this type of sensor, capacitive or inductive, they carry solid state devices inside. They have very good ingress protection. Okay, they range from IP65, 67, sometimes 68 also. Okay, so a few disadvantages which are there with this capacitive sensor. They are very sensitive to temperature because it changes the dielectric constant of air. Okay, so the range can vary. If you have tuned for certain distance, so with the increase or decrease in temperature, that distance may vary, and same is the reason it changes with humidity, because the permittivity which is there, that changes for the air which is there in front of it. Okay, so it can be triggered by dust, it can be triggered by moisture. This makes it little unreliable as compared to inductive type of sensor. Okay, and they are very, very sensitive to noise because it is a capacitor, just like your radio tuner, if you know it, they were also very, very sensitive. They works on capacitor, so any vibration in the plates will create unwanted triggering of this type of sensor. Okay, so they are sensitive to noise. It can turn it little unstable at times. So just they are normally placed on fixed installation. Yes, difficulty in designing, but hardly we do when we are in industry. This is for academician. Yes, to understand, yes, constructing such a fine-tuned circuit is really very, very difficult. Okay, so linearity is not good. So if you think that you can detect precise distance by tuning this, so it is not that linear to plan that. Okay, so they are not as accurate as inductive sensor. As you know, the way it works, they are not as accurate and sometimes not that reliable also because of these reasons. Okay, not just these, there are many other types of proximity sensors which are there in the industries. Few of them are photoelectric one. Photoelectric one is there in front of your mobile phones also. So So as it comes closer to your ear, your front screen that gets turned off. Okay, so that it doesn't detect any touch by your fingers or sometimes your cheeks and maybe your ear. Okay, so that is the reason. They are based on light reflection, and it can be tuned for color. That is the beauty of this, but not that accurately. Same color may have with different intensity will behave different. But yes, in industry, in a controlled environment, it can be tuned for color as well. So that is the beauty of it. And ultrasonic sensor, which are based on time of flight, it sends out the ultrasonic waves, and it just detects the reflected signal. They can also be used like a distance sensor to some extent. Yes, magnetic sensor, Hall effect sensor you have already seen earlier. So all these can behave like a proximity sensor. Okay. So yes, now moving ahead to a very wide kind of sensor, which is a force sensor, torque sensor, that can be used like an acceleration sensor also. So using the strain gauge one is a very common one, very rugged one, and since quite long time that is still there in the industry. And because industrial robots, they demand a rugged kind of sensor, so this is the one which is used. So it can go as high as 6 axis, which can detect forces in all the 3 directions and torque in all the 3 directions, orthogonal directions. So can be unidirectional also. So we'll just move on and we'll see how it is. So yes, what is this? This is nothing but a standard resistance coil, which is just arranged in a way like this. Okay, and from the top and from they are put in a sandwich kind of thing. Okay, so from the top there is a foil, and then you have resistance coil in between. You have another layer of foil which covers this inside, so that it doesn't get distorted or damaged. Okay, this is how it looks like. This is a resistive foil. So 2 leads are there, just like any other resistance, 2 leads are there. These are solder pads, or it may come pre-soldered with a wire extension so that you don't damage it. Okay, so overall it looks like this, and we call it a strain gauge or a strain gauge rosette. Okay, so how it works very, very simple. What it says, a basic theory behind this is change in resistance per unit resistance is now proportional to the strain which acts on it. Okay, so there is a constant of proportionality for this, that is known as a gauge factor. If you talk about gauge factor, it is change in resistance by total resistance of this gauge. So that is a constant anyway. So this is the strain which is acting. So gauge factor is defined like this. So normally when we buy such strain gauge rosette, normally they specify what is the gauge resistance for this and how much is the gauge factor. Normally it ranges from 0 to 2 gauge factor that is available in the market. So how it is mounted, how it works is very, very simple. So you may have a typical beam which is there. You can put your strain gauge sensor here, somewhere over here, and you have a fixed beam. Let us say it is a cantilever that I am trying to draw. So if it bends like this, you are having a force which is acting from here, so it will bend it like this. It will bend it like this. So what will happen? This strain gauge rosette, which is fixed on top of the beam, will see some kind of extension. Okay, it will be extended if it is put with an adhesive on top of that. So what it will do effectively is it will try to bend that beam. This force will try to bend this beam, and yes, you will see some extension in this, and that will change the resistance of this kind of wire. So extension, normally they will increase the resistance, whereas if it is compressed, if this strain gauge rosette is fitted somewhere over here at the bottom side of it, it will see compression. Okay, so if you compress, they reduce in the length of this is reduced, and effectively that will reduce the resistance. Okay, so this change in resistance is now used as a factor to detect any change which is acting on this beam. So this force is causing strain, this force is causing strain. So it can be tuned to detect precisely the force or the strain also. If you remember your strain formula, strain can be simply written like this. So modulus of elasticity is equal to stress upon strain. Okay. So stress is force per unit area and strain is strain. So you can call it as E, that is modulus of elasticity. Now if you simply rearrange this, it can be written like this. So what was your gauge factor? Gauge factor was change in resistance per unit resistance by strain. So you just substitute this strain here in this equation. What do you get? You get this. So this is your typical force which can be sensed by this kind of load cell. So you can detect force. Okay, for normally once the beam is made, so that cross section area is not going to change. Okay, Young's modulus of the material is not going to change. Okay, gauge factor, once the strain gauge rosette is chosen and it is put with an adhesive, that is not going to change. Total resistance of the gauge doesn't change. So what changes is force, okay, force which is changing, and what you see as an effect is resistance that is changing. So if you can detect change in resistance, you can detect force. So this is how this can be used like a force sensor also. Okay. So as an acceleration sensor, if you can detect force, you can detect acceleration, because acceleration is depending on force. M is constant, F is equal to M into A. M is a constant of proportionality here. So acceleration can be detected by measuring the force also. We have learnt it earlier also. Okay, it can detect many other parameters. So it can be mounted in a way where if there is any torsion in a beam, it can detect the change in resistance. Okay, you can mount this strain gauge rosette in such a way so that any torsion produced distortion in your some kind of beam element, and that can be picked up by change in resistance which is happening in your strain gauge. So normally it looks like this. This is a Siemens one. Okay, so inside of it you see there is a small beam with a strain gauge rosette which is fitted there. It is having a very nice enclosure with kind of diaphragm all over so that any water doesn't get in. Okay, so it is fixed within a strong housing so that whatever force which it is supposed to check, it doesn't get damaged with that force itself. Okay, if it hits somewhere else, it should not get damaged. Okay, so this is the place where load is to be applied. Okay, and there is a transmitting wire which can transmit that particular sensed signal to long distance. So it can detect torque, it can detect pressure, stress, flow rate. Okay, so any arrangement that can be made using this. So you just need to have an arrangement where that something which you are going to sense creates a distortion in this strain gauge, and that will create the change in resistance that you can pick up. Okay. So yes, moving ahead, so they are very, very accurate, almost 0.1% of the full scale. Let us say it is designed to be used with 0 to 100 kgs. Okay, then you should not see more than 1 kg of error. Okay, so that is quite big of an error, but yes, can be taken care of by having some other compensation mechanisms inside. These are readily available because they are just wire resistance. Okay, so they are very inexpensive and they are readily available, and the kind of enclosure which is the way it is made, they are very, very rigid in construction. It has a beam with an adhesive which mounts this strain gauge sensor. So once it is made, it hardly goes bad. It can see 10 to 15 years of life altogether. Yes, at times you may require recalibration. That is the issue with this. So yes, they are very bulky in size because the way it is constructed, it has a beam which cannot be made very compact. Okay, so they are bulky in size. Some conditioning circuit to make your data transfer to long distance, to pick up this change in resistance. So those conditioning circuits are there, which is a little costly but not very costly again. Okay, they require to be calibrated by the manufacturer when you buy it. Okay, so they sometimes provide you with calibration certificates. Okay, so that is very, very mandatory in industry when you use it. So even if you have seen this kind of thing, let me just switch to the applications. What this is electronic balance. Okay, you have seen this in the grocery store also when it is used, okay, for that particular kind of balance. Okay, and the way they are handling it, it is very, very bad, and still it works, you see. So that is proving that they are very, very rigid in construction. Once it is calibrated, at least for your grocery shop owners, they hardly get their calibration done once they buy it. Okay, so it may be very, very inaccurate that way. But in industry, when it is used, you have to go for recalibration because you want to work precisely. Your universal testing machine which is there in your lab, maybe that is using this kind of sensor. Dynamic suspension system in your automobiles that changes its behavior with the kind of road it sees. So that also uses this to check the kind of force oscillation that suspension is seeing. Okay, so to perform compliant manipulation tasks, a force sensor is required at the wrist of the robot. Normally it is fitted so that any object that it is handling, it comes to know immediately whether you have closed your gripper, but yes, it didn't pick up the object. So you immediately will come to know if you are also checking the weight that is getting increased if you are holding that object. Okay, so uncompliant manipulation, that kind of assembly task if your robot is doing. Okay, maybe cooperative manipulation if it is doing. Okay, so those kind of operation, they require this force sensor to be fitted, like grinding, polishing, buffing. So all the surface contact tasks where you require to have constant force which is to be maintained. Okay, that is there. So to perform any assembly task by any robot, so this force is to be sensed. Okay, to perform collaborative manipulation, for performing surgery, to give feedback of force is to be sensed. Okay, so that is why it is fitted. And to deliver a force feedback to user who is playing a game maybe. So a virtual environment force, this type of system can be used to handle something in virtual environment. You apply a force, that force is sensed and transmitted to the virtual environment to handle something. Okay, for virtual simulation and training system. Okay, so this is how a force sensor is designed and it is used. So let us move ahead with little higher variety of force sensor quickly. So now similar cantilever is, now you can see you have almost 1, 2, 3 and 4 strain gauge rosette. Why this is there, I tell you now. So they are fitted like this. So each of the beam of a Wheatstone bridge is now having this strain gauge rosette. Why so many? Okay, so let us talk about that. So under balanced condition of Wheatstone bridge, you know, if this by this equal to this by this, okay, this ratio is same. You see a zero voltage across these two terminals and no current flows through it. Okay, and V becomes equal to 0. This is the balanced case. So output voltage in case of unbalanced bridge, which is appearing over here, this voltage which appears here, Vs is the source which is applied. So those resistance, if it is not balanced, will produce a output voltage which is given by this. Now this is simple physics can be used to detect forces. Okay, they can be used to detect force, change in resistance or many other parameter like strain if you want to check. Okay, so why so many? So any change in temperature will cause change in resistance. If you at all have calibrated the way you fitted it here earlier, so you just had one sensor. If you have calibrated to see 5 Newton to see a kind of force, so with temperature, if this resistance has changed, so it may be 5.5 Newton, which creates the same kind of change in resistance. So that is not desirable. Okay, so once you have calibrated, it should be rough and tough as if the temperature change and the surrounding change, if it is to be considered to design any such force sensor or strain gauge sensor. So to compensate against those temperature changes, so this kind of arrangement is made. So let us just forget 4 of them, maybe just 2 of them should be good enough to do it. How, I'll tell you in different ways. So yes, there are various configuration in which this kind of strain gauge are fitted. One can be just quarter bridge, quarter means 1, 2, 3, 4, one of them can be used to mount this. Others can be simple, a balanced resistance. If your resistance is strain gauge resistance, let's say if it is of 20 ohm, fit 20 ohms to all 4 of them, all remaining 3 of the branches. Okay, one of them can just be your strain gauge. Okay, and VT stone is balanced. So if just one of them is changing, because that is the one which is mounted on the cantilever beam. So if that is changing its resistance, so that can be detected quickly by changing voltage which is appearing here. Okay, so that is, this configuration is known as a quarter bridge, but yes, this is sensitive to change in temperature. So if temperature varies, the behavior of this voltage changes. Okay, so that is not desirable. So there is another configuration which does most of the things for us. So yes, quarter bridge circuit with just, you don't have this, you have fixed resistance here, you have fixed resistance here, but 2 are there. One is your strain gauge, other one is a dummy one. This is just a dummy one. One of them is mounted on the cantilever beam, on this beam, but other one is just in the same environment it is kept, so that any change in temperature will cause a similar change in this as well as this. So sensor sees the change, and this dummy strain gauge will also see the similar change. So temperature change will not cause the, let's say balanced bridge has a component R1 by R4 should be equal to R2 by R3. So this anyway they will be constant, because that is a constant resistance which is there. So R4 is the dummy one. Okay, and this is your gauge one. This is your gauge. So if this sees a change by K times, so this also will see K times change in its resistance value. So ultimately they gets cancelled off. So any change which is caused because of temperature is linear in nature, so they get cancelled off. Ultimately the balance status remains balanced. So R1 by R4 is still the same. So whatever remaining change that you see in one of the branch R4 here, okay, if it is not the dummy one, so if this is changing, it is only change because of the forces which are there or the strain which is happening. Okay, so this completely takes care of the temperature change. Okay, so this is quarter bridge strain gauge circuit with temperature compensation. So with just one bridge that remains unstressed, and 2 of them were constant, 1 of them were used like a gauge. Okay, so there is another good arrangement. Let me just vanish to make things very simpler for you. So yes, this is a strain gauge circuit, half bridge strain gauge circuit. 2 are used, 2 of them are used. So sometimes the forces which are acting from outside, this may not be very huge enough, but you still want to see the change. So instead of changing just one branch of it, okay, you can have 2 branches. You can use the top branch that you see is in tensile loading, whereas the bottom one is in compressive loading. Okay, so one of them will extend, other one will get compressed. Okay, so this is how. So one of them will extend in length, while the other one will just contract. So the change in resistance will be twofold. One of them will see increase in resistance, whereas this one will see decrease in resistance. So effectively this balance status now, which is seen here. So R1 by R4, 2 changes will be there. One will be, let us say if you have fitted 2 and 3 here, as resistance, so both will change simultaneously. So that will affect the resistance twofold, and your Wheatstone bridge will be unbalanced significantly, and this voltage variation will be maximum. So that is the reason why one should use two strain gauges like a gauge. Okay, now one of them at the bottom side of the beam, other one at the top side of the beam. So enhance the amplification you want to see more. So in that case you can use. So it requires four of them, two dummy and two as a strain gauge. So that is this, and then final one is full bridge strain gauge circuit as shown in the figure. So yes, what do you see? This is in compression, this is in extension, compression and extension, that is because of tensile loading. So this is how it can be mounted, the way it is shown in this figure. Okay, so that is full. This is rarely used. This is the way you can see the maximum change in the voltage because of the forces which are there. But things makes very complex, because any problem with even a single one of them can make things very bad. So because they are glued with an adhesive, they are prone to get coming out due to the loading which is there. So this is a little uncertain here, that makes little unreliable. So that is the reason it is hardly used until unless it is deemedly required, because forces may be very small. You see, this is automatically compensated by temperature changes, because all four of them are getting equally affected by the temperature. So these are the four different configuration which is there. So I'll just quickly show you the formula how it works. So this is how a quarter bridge strain gauge configuration looks like. So the voltage change, if you substitute the values here, okay, you put the resistance, few of them are constants. So if it is constant, you can put same value to all these. Okay, if just one is changing, you put one, rest all are constant. So if you do that, you will see it comes out to be Vs by 4 delta R by R approximately. So this is there, and if you substitute your original formula for strain over here, so you see this one. So voltage which changes to force, it can be formulated like this. So only thing which is changing here is the force, and you see it as a change in voltage that comes out of it. So this type of bars are normally available even in many online robotics shop for your projects if you want to use. So you see it has a strain gauge which is fitted here, fitted with external wires which goes out, and it comes with a ready-made circuit which does amplification and transmission job for you. So yes, this is a quarter bridge configuration, and you see voltage which is proportional to F. G is 2, gauge factor is normally 2 for this type of foil strain gauge for most of the gauges which are available. So if it is not known, you can take it as 2. Okay, modulus of elasticity, this is a well-known formula, you know it already. So if it is a full bridge circuit, this is the case. So change in resistance per unit resistance for different resistances are here. This is how it will look like, and in terms of strain it is written like this. Okay, I won't get into the derivation part of it much, because this is beyond the scope also, but yes, it can be readily used if you are from industry, if you are a project student, maybe in research. For half bridge system, for configurations which are here, so you can have in 4 or 1 or 3 or 1, you can put your strain gauge. In that case, this and this or this turns out to be 0. Okay, in that case, you just substitute them, you will get the end formula for output voltage in terms of the applied force. So that as a function of force you can get. So yes, this can be used like a torque sensor. So you can have a beam, where your strain gauge rosette is fitted like this, okay, at different places on the torsional beam. So this can detect the torque, so it can see the change in torque. So yes, it can also see the force if it comes from here. So this is any change in torque also will cause change in this, as well as change in force can also be picked up. So if it is just mounted like this, it can just detect the torque. So if it is fitted like this, it can just detect the torque. There is some linking between the force and torque also. We'll see it later in other slides now. Okay, let me come back. So this is it. So yes, there are many sources of error in these kind of load cell design, commonly known as load cell, not like a force sensor, and use also. While using, you have to be more careful, because most of the time you buy such force sensor, normally you don't design this kind of sensor. So forget about rest of the things, but this is very, very important. If someone is very interested, they can go through this also. But yes, yes, improper loading. If you believe that your force is going to come from this direction, your force cell load cell should be mounted like this. If it is inclined even by a degree, it will give you an incorrect reading. And if at all you still want to go ahead with that, you go for recalibration of that. So orientation error in mounting can give you improper results. Okay. So any electromagnetic induction nearby, because you know it is a kind of circuit which is there inside, so they are prone to get affected by any external electromagnetic signal. So this should be kept very well apart. Normally the kind of sensor I showed you, which was an industrial sensor, so it was protected from all around using a metallic casing so that it doesn't get affected by EMI. Okay. So isolation and using a carrier frequency as an amplifier are better way to use it, but that also is taken care of by the manufacturer of this kind of force sensor. Okay, so that is there. Calibration issues are there, because over the period of time your beam changes its behavior. The kind of adhesive that changes of its behavior. Maybe strain gauge also has changed. So it requires calibration maybe every 1 year or 2 years, you have to go for it. So yes, the calibration issue is there, and dependency on various gauge fixtures is always there. Okay, the way it is fitted. So you have to go for, even if it is mounted somewhere, that mounting is to be checked every now and then. So yes, effect of temperature you see, but that can be easily taken care of by fitting dummy resistance, you know. But yes, by huge lot of change if it is there in temperature, so resistivity is changing, not the resistance is just which is changing, which is getting cancelled off. So that is large temperature change effect should be taken care of. Okay. So there are many other which are listed here. I won't get into this, but yes, you can simply go through this if you are interested. But in industry normally we see these kind of errors which should be taken care of. Okay, now just look at how 6 degrees of freedom force sensor are designed and used. Okay, so yes, you have a different, let's say you don't just have, let us just give you an example. Let's say you have a beam which is like this. Okay, now you are not just fitting a strain gauge in one of them. Okay, so this is your a beam. Okay, this is your design of beam. So you may be fitting your strain gauge here, you are also fitting a strain gauge here. So in this case what will happen, at least any application of force in this direction will be picked up by these two. This is mostly, this one a bit also will change. Okay, so any change in force in this will change both of them. Any change in force along this direction will also change these two strain gauge voltages. Okay, so it will give you some change in this and this also. So this time this will change more and this will change less. Okay, so you got it. What I am trying to say is, so this can be arranged like, so voltage to the two voltages which are coming out of each. Let's say this is 1, this is 2. So this is 1, this is 2. So two voltage can be linked with constant like K1, K2, K3 and K4 to give you a force along X and force along Y. So this is a simple relation which can give you the forces that is appearing on those branches. Okay. So basically this is 6 different gauges are fitted. So this is for a 6 degrees of freedom load cell, where you have 3 branches, and in those branches you have 3 load cells which are fitted in, that is to detect force, and 3 for the moments. Okay, so and then it can be related like this. So it can detect moments along all the 3 axes and forces along all the 3 axes. But anything which is appearing, any external force or moment which is appearing, changing all the voltages, not just one of them. So that is the reason you have a matrix. This is known as a gauge calibration matrix, which is provided by this kind of load cell manufacturer. Okay, 6 degree of freedom cell manufacturer. So yes, they are made like this, and you see this is a load cell made by TEDs. So these voltages are appearing here. All the 6 is arranged here, and they can be transmitted, and you have this gauge calibration matrix which is provided by the manufacturer. Simply have this voltage array over here, this matrix over here, and you can calculate your force and the moment which is appearing. So these kind of sensors are mounted at top of the wrist of your robot, so that you can see the forces and moments. Okay, so gauge calibration matrix is to be recalibrated every maybe 1 year, that as prescribed by the manufacturer, and then it can be used very precisely to do any compliant manipulation, assembly, just like your task, like surface finishing task and those kind of tasks. Okay, so that's all for force sensor and proximity sensors and sensors altogether. We'll discuss. So this is just a representative picture which is there. I have taken it from here. Okay, you can just look at it. So yes, finishing this. So in the next class, we'll see some leftover portion, that is limit switch and classification and characterization of this kind of sensors, any sensors. So it needs to be classified so that you can select proper one of them if you want to use, and characterization. That is the most important part of next class. That is what all parameters which are listed in a data sheet, if at all you find one such sensor. Okay, so we'll talk about all of those in the next class. That's all. Thanks for today.